Good morning, good afternoon, good evening, and welcome to a post on dirac, penrose, and wolfram. By the standards of the physics community, Paul Dirac is the tops because he hated poetry, and only the manliest of men hated poetry as much as Paul Dirac did. Physics is only really good when it is masculine, and when it proclaims that only math is beautiful. Paul Dirac was exemplary in all of these respects. He was so masculine that women frightened him. Heisenberg took him out to go dancing with some nice girls, and Dirac skeptically asked him, "How do you know which ones are nice?" Here are some quotes from Paul Dirac. God used beautiful mathematics to create the world. Pick a flower on earth and you move the farthest star. I do not see how a man can work on the frontiers of physics and write poetry. They are in opposition. In science, one tries to tell people in such a way as to be understood by everyone something that no one ever knew before. But in poetry, it's the exact opposite. So he had a sense of humor. The flower, earth, and star quote makes me think that he tried to write poetry but wasn't very good at it. And the last quote suggests to me that he read someone's poem and didn't understand it. He sure was good at math, though. He was so good at it that he didn't really believe in the interpretation of the equation which won him his Nobel Prize. I happen to agree with him on this point. I think that antimatter is a rather stupid, redundant interpretation that lacks perspective. When a person attempts to reduce physics to its essence, the language or conceptual basis they choose shouldn't impact the result that much. Yet, despite our best efforts, it always does. When Dirac mused about the most fundamental concepts, he did so in his favorite language, math. He wrote in Scientific American, in an article called The Evolution of the Physicist's Picture of Nature. The physics of the future, of course, cannot have three quantities, h bar, E, and C, all as fundamental quantities. Only two of them can be fundamental, and the third must be derived from those two. It is almost certain that C will be one of the two fundamental ones. The velocity of light, c, is so important in the four-dimensional picture, and it plays such a fundamental role in the special theory of relativity, correlating our units of space and time, that it has to be fundamental. Then we are faced with the fact that the two quantities h bar and E, one will be fundamental and the other will be derived. If h bar is fundamental, E will have to be explained in some way in terms of the square root of h bar, and it seems most unlikely that any fundamental theory can give E in terms of a square root, since square roots do not occur in basic equations. It is much more likely that E will be the fundamental quantity and that h bar will be explained in terms of c squared. There will be no square root in the basic equations. I think one is on safe ground if one makes the guess that in the physical picture we shall have at some future stage, E and C will be fundamental quantities and h bar will be derived. Thank you, Paul Dirac. Mathematics is, of course, a product of geometry and philosophy, in which the fundamental things in the universe are defined by motion that occurs in circles and lines, while nothings are defined by the difference between the positions of the centers of the circles that define the things. From what Dirac wrote, I see that the speed of light, c, defines the maximum possible rate of motion in a line, and that the charge, E, defines the circumference of a circle produced by something that travels in a circle at the speed of light. This is the smallest possible circle and the maximum amount of energy or mass that can be concentrated in a given space. And if you are able to express this concept in the language of Lie algebra and Green's functions and such, you can win the Yang-Mills Millennium Prize. But they don't give you a prize for explaining these things in non-coded language. I am going to continue speaking in plain speech, non-coded language. Circulation and vibration define a spherical space with a minimum volume given by Planck's constant and a radius determined by a point's position and momentum changes. This is a way to describe the uncertainty principle, and it is why Planck's constant is the smallest distance change that can occur for a given momentum change, or the smallest momentum change that can occur for a given position change. Since the area of the circle is related to the circumference, that is why Planck's constant is equal to the speed of light times the mass and radius of the proton, and why this constant can be derived from the charge E. To get a deeper understanding, it is useful to understand how surfaces and volumes relate to each other regarding rotation. A nice way to connect this to special relativity is to notice that a bubble or a charge will turn into a pancake in its direction of travel. Because the circumference stays the same, despite being squished, the circulation of fluid around the bubble or of current around the charge has to slow down, and this is time dilation. To connect this to gravity by way of general relativity and the uncertainty principle, one requires a simple heuristic. There is an attraction when vibrating objects move together, and repulsion when they move in opposition. There is an attraction when objects circulate in opposite directions, and repulsion when they circulate in the same direction. Circulation and vibration define a spherical space with a minimum volume given by Planck's constant, and a radius determined by the center's position and momentum. This is a way to describe the uncertainty principle. The number of such spheres in a given space determines the density and the amount of uncertainty present. Denser, more curved space will be heavier, more uncertain, and have a stronger gravitational field. It will also bend light more, and then less dense, less uncertain space. The more uncertain space is, the more power it has to change the course of things. This is why uncertainty is critical for an understanding of gravity. And if you think about it, the speed of light, although fundamental, depends on the material through which the wave travels, and a gravitational wave is a sort of material made up of magnetic monopoles, or equivalently, Dirac's sea of negative energy particles. The gravitational field does still seem to require the definition of another fundamental constant that describes the friction coefficient related to the transfer of energy between matter, circles, and waves, linear motion. Since this has to be quantized, it would need to involve the collapse of the smallest circles into lines, and it must be connected to Boltzmann's constant. But I haven't completely worked this out geometrically yet. I don't think it's that complicated. That is what I can scrape together from Dirac. He had a geometric understanding of the world, and he encoded it with equations. Penrose, who came after him, had a geometric and recursive understanding of the world, and he encoded it with pictures that looked sometimes like doilies. Lots of tiling and recursive patterns. In more recent years, Wolfram developed a geometric recursive understanding of physics, and he encoded it with an algorithm that I'll get to after I finish with Penrose. I like to think that I have a similar understanding which I encode in plain English, but I'll let you be the judge of that. From Penrose's pictures, I gather that the transition from taus to muons to electrons or from generation 3 to generation 2 to generation 1 particles seems like a state change as layers are melted away from a decelerating particle, as in a melting snowflake or a molecule breaking apart. In a Riemannian relativistic system, the faster that something moves, the colder it acts after all. Each generation of particles has the same charge and spin, but a different lifetime within Riemannian space. A world where lengths contract and time dilates depending on your relative velocity. But what if changing one's perspective to that of a god-like Cartesian in absolute space shows that the lifetimes of particles are all the same, but the charges are different because they are spinning by different amounts relative to an absolute coordinate system? What if Riemannian and Cartesian vantages provide different yet equivalent ways to describe the same system? A godlike Cartesian perspective would see that we have chosen to approximate things in Riemannian space as being in a steady state, in which they all spin by the same amount, and therefore all have the same charge. The Cartesian would see motion that we cannot see, because we are trapped in a non-inertial reference frame, moving in sync with the things around us. The Cartesian would see that particles don't just pop into and out of existence as in the standard model. They exist in a permanent state, but their spin and charge change and make them appear and disappear from our perspective. After all, we can't see things that are out of phase with our particles, even if they must exist for our world to function in the way it does. In the most simplified language I can extract from this chain of thought, the things we see are in sync with us, and the things we feel are out of sync with us. A Riemannian person indoctrinated in accordance with the standard model might insist that these ideas are inconsistent with conservation of charge, but I would say that when you change your perspective, charge will still be conserved. The charges and lifetimes of what you see will just look different. Likewise, standard model people tend to react badly to the idea that spin up and spin down electrons are the same thing as electrons and positrons. They say that shifting one's perspective from outside of an atom to inside of an atom seems to violate charge conservation, but they're wrong. Charge conservation within each perspective is conserved. Charge is conserved within each perspective. A god can shift its perspective at will, and even if we can't do measurements with an absolute godlike perspective, we can certainly imagine doing so. This was in my mind when I saw the work of an engineer named Mark Morris, who described the difference between the 3 generations of fundamental particles in terms of the number of dipoles contained within each particle. He had figured out a sort of a way to assemble all of the fundamental particles like Legos based on smaller components that he called electrinos and positrinos. In his world, generation 1 has 3 dipoles and is the most stable. Generation 2 has 2 dipoles, and generation 3 has only 1 dipole and is the least stable. If you look back at some drawings that Penrose drew, you kind of get a sense of a similar picture that was expressed in drawings rather than in words. These objects, which might have been called magnetic monopoles in a Cartesian world, are connected to a Riemannian cosmos with an unmeasurable dynamic conversion factor that he calls a shell. I believe that it is similar to the concept of an axion from Helen Quinn. I hadn't heard this story in this form before, and I found it interesting. However, I do think that Mark's view of particle physics as a whole is largely a repackaging of some old ideas, but that's inevitable whenever you do anything in physics. His unmeasurable electrino-positrino pairs filling a space-time gas sound like the same thing as an ether filled with magnetic monopoles or a dirac sea of negative energy particles. Electrino-positrino pairs are just dipoles, and a magnetic monopole that moves is also just a dipole. Why aren't they two ways to say the same thing? If you imagine that the object is stationary, it is a monopole, and if you imagine that it is moving, it is a dipole. He calls his vision neoclassical physics, and it makes sense that he and I crossed intellectual paths, because the accelerator physics that I studied is basically classical particle physics. I've learned that in the larger physics community, accelerator physicists like me are much like Benedictine monks within the Catholic Church. They compose an old order that is somewhat disconnected from modern physics, and there is a lot of overlap with the Order of Engineers, by whom Mark was trained. His formalism is, in many ways, a simplified version of modern particle physics or string theory, condensed such that only the foundational concepts might propagate into the future, absent all of the complex spandrels. He runs into resistance from young physicists today who are unable to understand theories they've learned in slightly different languages. In essence, they show no signs that they understand the coded languages they have been taught to speak, at least most of them. If you understand the statement that a Poincaré disk is a relativistic approximation of an absolute hyperbolic reality, and that the step size you take depends on your velocity, I think you already have pretty much enough to decrypt the languages of modern physics. De-encrypt. Decrypt? Yeah, I don't know. If I translate the unmeasurable conversion factors between Cartesian and Riemannian space into more fluid terminology, I see that a transverse wave can be approximated by a spinning sphere tumbling through space, much like a generation 3 particle, an oversized bubble that tends to break apart into two smaller bubbles and some light. Those two smaller bubbles are spinning in opposite directions and thus glued together in a generation 2 particle as they continue to tumble through space. But they are unstable because the angles at which energy must circulate between them are too sharp. This is why two bubbles break up into 3 to form a generation 1 particle. Triangles are especially stable objects, and 30, 60, 90 triangles fit together quite nicely to make an isosceles triangle, a clock, or a Poincaré disk. If this story sounds similar to that of hydrogen, I imagine that it should, if physics is as recursive or self-similar as it seems to be. Generation 1 is analogous to n equals 1. Generation 2 is analogous to n equals 2 in a hydrogen atom, and generation 3 is like n equals 3. You might recall that there is no stable n equals 4 shell within hydrogen, just as there is no stable generation 4 that's been measured at all. People have claimed to measure n equals 4, but it's never stable. So does it really exist? I don't think so. These rules also probably apply on the scale of the solar system, but we can't see these quantized patterns because the time scales we can observe are too short to see them. On an earthly scale, we can get a lot of information about the Schumann resonances, but still see the limits of our predictive power. One might have a perfectly accurate classical deterministic set of equations for existence within a non-inertial oscillating reference frame, but if you can't know the initial conditions, all of your predictions will have a certain degree of uncertainty in a quantum sense. Of course, if the electron is made of 3 dipoles in Cartesian space, it should have a net dipole moment, but it doesn't. And I think this tells us that nothing is ever truly stationary in a Cartesian space, because the space itself is in motion. Well, at least from a godlike perspective. An electron that doesn't move is modeled as a monopole, but when it moves, it gets a dipole moment. Thus, a Cartesian space filled with magnetic monopoles doesn't objectively exist other than as an approximation and useful heuristic. Then again, when the map is not the territory, that is all physics will ever be, a comforting heuristic and a sequential approximation of simultaneous processes. I think it's worth taking a moment to think about the purpose of physics, and I think that it is a useful tool to teach people how to think when it is taught properly. But if you look at modern physics today, it utterly fails in that purpose. So I think we should get back to, the foundations and reconnect physics to philosophy and stop making physics a way of tying people's minds in knots and recreate it as a tool for teaching people how to think analytically. That's all it should be. If you're finding yourself trying to hold contradictory ideas in your mind at the same time and that you have to speak in counterintuitive languages, I think that the discipline is broken and you got to go back to a state where it worked. That's always what you do in a program. If you're writing a program or something, if you break it, you just go back a few steps and start teaching from an older book. Next up, I'll talk about Wolfram. He wrote this nice software called Mathematica. He took these sorts of geometric recursive ideas from Penrose and dirac, and he encoded them in a simple algorithm. But instead of writing about electrinos and positrinos like Mark, the engineer, he writes about oligons and a universe of fundamental particles that are 10 to the 37 times smaller than the electron, whereas Mark speculates about what might be one layer deeper than the fundamental particles we have measured. Wolfram speculates about a universe of layers below what we have been able to measure. And as long as they make testable predictions, they are doing better than the community of string theorists, which compose the mainstream of academic theoretical physics. Since none of them are making useful predictions, I conclude that they are all just inventing different types of Legos that can be used to construct the fundamental particles which have been measured. How might one decide on the best set of Legos is a valid question. Should they be bubbles that stick together, square blocks with state vectors as in a video game, or should they be triangular tiles? If all of these shapes can be used to recreate the world of fundamental particles, one might argue that none of them are of any use, or one might argue that the largest, most efficient building blocks should be chosen based on aesthetic grounds. Perhaps the most efficient building blocks create nice geometric patterns when they are put together, while less efficient blocks create more amorphous shapes. These questions do not keep me up at night, but there are mathematicians who can spend an entire lifetime wandering around in such geometrical wonderlands, and sometimes their ideas find useful applications. However, you have to recall that since the atomic bomb was built, the field of physics was subsidized on a level that was completely unsustainable, and instead of allowing the field to flourish, it instead created a mountain of rubbish. There's just too much noise. The good stuff couldn't be filtered out anymore, and now it's buried under a pile of trash. That's what happens if you over-subsidize an academic discipline. I like to think that all of these people I've mentioned are all saying similar things in different languages, and that I share their geometric, recursive understanding of the world. The main difference is that I encode it in plain, everyday words rather than math, pictures, or algorithms. In the past, everyday words might have been an unacceptable form of academic encryption because some ideas are not for everyone. But today, so few people understand even plain English, especially physicists, that I think that what I'm doing is okay. In 30 years, someone may develop this same geometric recursive understanding and encode it in memes or pictures. Scary. I met one fellow recently who believed that all of physics could be understood or encoded through videos of fluids taken with high frame rates. I can certainly imagine that in a future without language, video clips may be how people communicate. I'm writing a novel about a world in which language is a dying art, and for research, I've read stories about feral children who've spent their first 12 years without ever being spoken to. They understood physical gestures, but they could never learn to use much more than very short, rudimentary sentences. And I think about children being raised on video games and wonder how their communication skills are being impacted. I mean, just within my lifetime, I notice a change in the accent that is spoken in the US. So I left the States back in the early 2000s, and now I listen to YouTube videos and there's a change in the accent. Maybe those who live there can't hear it, but because I've been living in Germany, I listen to the voices and I think the millennials sound different. I mean, it's not like these local accents where you had the Valley Girl accent spring up in California. It's strange to hear. There's definitely a change in the accent in the last 20 years since the internet. The level of cultural advancement tends to correlate with the richness of the language, and maybe a video clip-based language might someday be richer than our present-day word-based language. It's a frightening concept, but it's possible. The disapproving elephant in the room with dirac, penrose, wolfram, and meme GIF physics is, of course, string theory and standard model LCDM physics. Their community has been getting a lot of flack lately for being unnecessarily complicated, too untestable, too obsessed with beauty, etc. But I don't think that they are alone in that boat. I'll leave that to others to fight about. I would rather write some novels, and I encourage you to take a look at them because they take a look at scientific culture and the limits of what we can know. Thank you for watching. I hope you tune into my next videos.